Okay, so let's see where we are at this point. So we said that the system AX equal to B either has 0, 1, or an infinite number of solutions. And we said that we know everything basically there is to know, and we have exactly one solution. We know the conditions under which we'll get exactly one solution, and we know what the solution looks like. And we also dealt with the case of an infinite number of solutions. We know when we're going to get an infinite number of solutions. In the last couple of videos we showed that occurs when the number of linearly independent rows is less than n, the number of columns. And we saw what the solution looked like. It's a particular solution plus basically a linear combination of the kernel basis vectors. So now we're at this third case, which is when we don't have a solution. And we said before that we have an intuitive notion of when we're going to get this sort of situation. We looked at this example and we said, when we have a row echelon form of a coefficient matrix A where the row is entirely consisting of zeros, but the right hand side for that row is non-zero, we can't have a solution. And we want to verify that's when we are going to get zero solutions. But we also want to know, well, what do we do? If there's no solution, how can we solve this problem? And the truth is that these sorts of systems occur a great deal in regression. And what we're going to see is that our solution is basically going to be the vector AX that is closest to B. So we're going to try to find the vector X such that AX is the closest to B. And that's going to be our best approximate solution. Okay, so let's kind of look at what we're doing here. We're going to first of all notice that the problems are going to occur mostly when the number of rows are greater than the number of columns. This is an overdetermined system, and for such systems we generally won't have a solution. We say that the system is inconsistent. The only time we will have a solution when the number of rows is greater than the number of columns is if there are a lot of linearly dependent rows. After you do Gaussian elimination, basically the number of linearly independent rows has to be less than or equal to the number of columns. Okay, in any case, there is an example of a system that is always overdetermined, and this is when we do simple linear regression. And in fact, basically any linear model is always going to have this problem. So we know that the statistical model for simple linear regression is where we have a response variable y that we want to predict from some predictor variable x. And so the problem is that there's noise in this equation that generally come from some sort of normal distribution. And so of course we collect a whole lot of data points. So if we collect m data points, where we get the following system of equations. And you can see that there are too many equations for the number of unknowns. Okay, whether or not we know the epsilon, that's irrelevant, because you notice that if I do Gaussian elimination, okay, the first row, the first column automatically becomes all zeros except the 1, 1 position in this coefficient matrix. And so then all I have to do is just use this one to clear off all the others, and you can see automatically that if all of these do not become zero when I do the row reduction, I'm going to have problems, and they almost never will. In any case, we go ahead and we use the observed values of y, and we get a matrix, equation that looks like this, okay, where the vector beta is the beta naught beta 1 that we're trying to solve for. Okay. Now, what is the solution? How do we get a solution to this? Okay, well, the idea, like I said before, is we want to find the vector x that makes AX as close as possible to B. And so we could write our solution in a mathematical form like this. It's going to be the x that minimizes, it's the x that is the argument in this function and minimizes the norm of AX minus B. That's going to be our solution. Now before we can look at this solution, we have to introduce some terms, and I want to make an observation. You notice that in the case where we have an infinite number of solutions, the row space of A played a fundamental role, right? The row space of A and the kernel of A were the main subspaces we were interested in. When we have the case of zero solutions, it's not the row space, but the column space of A that's going to be important. And we've already defined what that is. That's the span of the columns of A. And the reason why is the columns of A determine what B's we can have a solution for. And so we're going to introduce this new term called the range of A. And the range of A is basically all of the right-hand side vectors for which AX equal to B has a solution. And we're going to show a really key fundamental fact now that's very important, which is that the range of A is equal to the column space of A. And this is such an important theorem, I want to prove this. So let's suppose A is an m by n matrix. Then B is in the range of A if and only if there is some x in Rn such that AX equal B has a solution. So I can write down the system of equations. Now we recall that when we multiply a matrix by a vector, we can rewrite that as a linear combination of the columns of A, where the coefficients are the components of X. So now you can see very, very clearly that B is a linear combination of the columns of A. Therefore, this is true if and only if B is in the span of the columns of A, which is true if and only if it's in the column space of A, because that's what the column space of A is, by definition. So you notice something very important, which is that the linear system AX equal to B can only have a solution. In fact, it's an if and only if statement. If B can be written as a linear combination of the columns of A. That's a very important fact. So how are we going to use this information to get a solution? We still haven't gotten anywhere in this problem, right? Well, here's kind of the outline of what we're going to do in the next video. We're going to say, let me just put everything up. We're going to say, well, if AX equal to B had a solution, then B would be in the column space of A, and we wouldn't have any problem. We could find that just by, whatever method we wanted, LU decomposition, Gaussian elimination, whatever. But if it doesn't have a solution, then we're going to find the vector B prime that's in the column space of A that's closest to B. Notice that B prime has to be in the column space of A, because if it's not, we can't solve for X, okay? And so which B prime would we want? We'd want the one closest to B, right? That would be the best solution. And what we're going to show, and this is not obvious, okay? We're going to show that when we project B onto the column space of A, and that projection is going to be our B prime. And we really haven't talked about projections of vectors onto columns, onto subspaces, so I'm going to discuss this, okay? But this is the rationale. And what we're going to show is we're going to show two things. First, we're going to show that when we project a vector onto a subspace, the projection lies in that subspace. That's kind of obvious, okay? And we're also going to show that that projection is the closest element in the space to that vector. Okay? So the projection of B prime, will be the closest, will be the element in the column space of A that's closest to B. And so now we're going to solve instead the equation AX equal to B prime for X. And that's going to be the best solution that we can achieve. And we're going to see how to do that in the next video.